Good day, everyone. My name is Dario Guidotti from the University of Sassari. In this presentation, I will be discussing some of our recent work on the formal verification of neural networks used for object detection within the automotive domain. As you are likely aware, neural networks have been successfully applied across various domains within computer science. Nevertheless, their deployment in safety and security critical contexts remains somewhat limited due to the absence of formal guarantees regarding their behavior. Furthermore, since 2014, neural networks have been demonstrated to be subject to several reliability issues, the most notable being their vulnerability to adversarial perturbations. To address these concerns, our research explores how formal verification can be utilized to certify and enhance the reliability of neural networks employed in vehicle detection. This research has received funding through AIDOaRT, an Excel project started in April 2021, involving 32 organizations from 7 different countries. The aim of this project is to enhance the system engineering life cycle for cyber-physical systems using AI augmented automation. One of our case studies within the project was proposed by Abinsula, a Sardinian company that provides innovative ICT solutions globally for the automotive sector. The case study centered on an electronic rear-view mirror augmented with cameras and AI to improve driving safety through alerts and suggestions. Our focus is to enhance and certify the reliability and trustworthiness of the AI system, particularly of the neural networks used in this case study. The reliability of neural networks in such applications is crucial for the safety of autonomous vehicles, as drivers could be misled by erroneous alerts or suggestions, potentially causing harm to other vehicles or individuals. Furthermore, it has been demonstrated that real-life adversarial attacks, such as the one illustrated in the lower images, are feasible. Small stickers placed on a stop sign can cause an object detection neural network to misclassify it as another signal, or fail to detect it entirely. Since the discovery of these reliability issues, formal verification has emerged as a potential solution, as it allows for the certification of the robustness of neural networks against this kind of adversarial perturbations. While a substantial amount of research has been conducted since the first paper on formal verification of neural networks, verifying current state-of-the-art models remain highly challenging. Specifically, state-of-the-art verification methodologies lack scalability and are still unable to support the full range of modern neural network architectures. For instance, the YOLO object detection neural networks, whose first version dates back to 2015, are only verifiable by a limited number of tools and only in their smallest version and for very specific properties. Let me provide some background on the neural networks considered in this work. Traditionally, the architecture of neural network used in computer vision tasks can be divided into components, a feature extractor and a classifier, or, in our case, a detector. The feature extractor component takes a raw input image and extracts relevant features from it, representing them as a vector of numbers. This component can be seen as analogous to traditional feature extraction methodologies like SIFT, but it has the advantage of autonomously learn how to extract relevant features. The subsequent component uses these features to complete the task of interest, whether it be classifying the image or detecting an object within it. Our proposed approach involves using, alongside an object detection model, a less complex but verifiable classifier model to serve as a step zero safety net in object detection. When possible, the two models would share the feature extractor component, therefore reducing the strain on computational resources. The idea is that, if we have an image containing a car, the classifier will simply indicate whether the image represents a vehicle, while the detector will provide its bounding box. If the trustworthy classifier detects a car, but the detector does not, an alarm can signal the problem to the driver, thereby avoiding potentially dangerous errors. As a preliminary experimental evaluation of our proposed approach, we focused on developing and verifying the classifier component of our system. The dataset considered is the vehicle detection image set, available on Kaggle. This dataset consists of 17,760 color images with a resolution of 64 by 64 pixels, divided into the classes vehicle and non-vehicle. On the slides, you can see some examples of the images belonging to the respective classes. The models considered in our experimental evaluation all present the same feature extractor component architecture, consisting of 6 consecutive blocks. Each block is component of a convolutional layer with ReLU activation functions, followed by a max pooling layer. The feature extractor takes the raw image as input and decomposes it into a vector of 1024 numerical features, which is then provided as an input to the classifier component. For more detailed information regarding the architecture of the feature extractor, we refer you to our paper, as it is not the main focus of the experimental evaluation. The classifiers all share an analogous architecture. Each is composed of 2 fully connected layers with ReLU activation functions, followed by a linear output layer with identity activation. However, they differ in the number of neurons in the 2 fully connected layers. The first has 64 and 32 neurons respectively, the second has 128 and 64, and the third has 256 and 128 respectively. On the slide, you can see the identifiers we used for the models in reporting our results. The properties considered were instances of local robustness. This type of property formalizes the concept that, if a certain image is considered as input for a neural network of interest, small variations applied to such an image must not cause the network to misclassify it. This safety property can be formalized, as shown on the slide, by considering all the possible variations of the image whose infinity norm is bounded by a certain value epsilon, and imposing that all of them are classified in the same way as the initial image. However, universal quantification makes verification undecidable. Therefore, we need to reformulate this property as its negation. That is, we need to check if there exists a perturbed image such that the network misclassifies it. Here is a brief overview of our training setup. To train and validate our models, we utilized Pinever, a comprehensive tool designed for managing, training, and verifying neural networks. During our training process, we employed the Adam optimizer with a learning rate set to 0.001 over 25 epochs, using cross-entropy loss. Additionally, we used the learning rate scheduler that halved the learning rate after 5 epochs without a reduction in validation loss. We partitioned our dataset such that 20% was allocated for testing, and of the remaining data, 30% was allocated for validation purposes. The batch size was set to 128 for training and 64 for validation. The verification process leveraged the over-approximate version of the algorithm provided by Pinever. This algorithm employs abstract interpretation to generate an over-approximation of the neural network's output for all potentially perturbed images, relevant to our specific property. If this over-approximated output does not satisfy the negation of the safety property, It indicates that no unsafe data points were identified, thereby confirming the validity of the safety property. In this table, we present the results of our experiments. It is evident that all the models considered achieved satisfactory accuracy, with even the least performing model achieving 99.92% of accuracy. Interestingly, the larger model did not always outperform the others. Regarding verification, we assessed 3 different epsilon values, each corresponding to different properties and representing varying magnitudes of perturbations. Across all models and epsilon values, PyNever successfully verified the specified property within the 10 minutes timeout, demonstrating local robustness against the adversarial perturbation considered for all the models of interest. However, it should be noted that verification time increased significantly with larger network sizes and higher epsilon values, as is particularly evident in the last model. Summarizing, we proposed a novel approach for enhancing the reliability of automotive object detection systems. We designed and carried out a preliminary experimental evaluation focusing on proving the accuracy and verifiability of the Step 0 models. The results showed that the models reached satisfactory accuracy and could still be verified in reasonable time using PyNever, a state-of-the-art verification tool. Now we are focusing on extending our experimental evaluation by considering more realistic scenario in which to test the complete system composed by the Step 0 and the object detection models. We would also like to expand our work to more complex and significant properties and eventually adversarial perturbations. Finally, while verification can provide formal guarantees on the reliability of a neural network, it cannot increase the reliability of an unreliable neural networks on its own. Therefore, we would also like to investigate techniques like safe training and repair. Thank you very much for your attention.